So let's start with JEE Advanced. Okay. Advanced 2025. See, the first thing is the notification for application form has already been there. You can fill up your application form from 23rd April to 2nd May. Okay. 23rd April to 2nd May. So you get a window of 10 days around. Then fine. Now the second thing that I want to say is the 75% criteria is still applicable. Okay, it's not going anywhere. Don't go into rumors and kind of thing. And what are the other things? Okay, so let's start with the question. Okay. So this will be the fourth lecture on the chapter of gravitation. Okay. See, the questions I'm doing from irodov are very important from the perspective of JEE Advanced. Okay. So if you have scored around 98 to 99 percentile on your mains, okay, just start preparing for this question. Okay. So without any further nonsense, let's start with the question. So in this question, we're at question 217. We completed question 217 in the previous lecture. In this lecture, we'll start with question number 218. So in this question, what the question has said is that there is a planet, a central planet, let's say Earth. Okay. And two satellites are revolving around Earth. Okay, in a circular orbit. Two satellites are revolving around Earth in a circular orbit. So then fine. Now the question is asking what is the time period of second satellite around first satellite? So you might be asking, sir, aren't the satellite rotating around the Earth? Satellite 1 is also rotating around Earth, satellite 2 is also rotating around Earth. So how come satellite 2 is rotating around 1? Or how come we find out time period where satellite 2 is rotating around 1? See, if you recall the problems in Newton's law of motions, especially Coriolis forces, there I said certain something. Suppose a disk rotates with angular velocity omega. Okay, this is a disk, this rotates with angular velocity omega. Any 2 points would also rotate with respect to each other with same angular velocity omega. That's what I said, isn't it? Same type of concepts apply out here. Okay. Suppose this is rotating, this is moving in this direction. Okay. This satellite is moving in this direction. Both the satellites are moving up. Okay. See. Suppose both are moving with same angular velocity. That means what? Both will move like this, isn't it? Consider this tip to be satellite 1 and this tip to be satellite 2. Suppose both are moving like this. Okay. Can you see the rotation? If you just observe satellite 1 and satellite 2, they seem to be rotating, no? See? They seem to be rotating. Okay. In this case, omega 1 will be much greater than omega 2. Why? Because planet 1 or satellite 1 is much nearer to Earth, so it will have a larger angular velocity. So even if one goes faster than 2, even if both are going up, then also some kind of rotation happens. Can you see the rotation? Okay. So in that case of relative rotation, suppose the observer is at planet 1. Satellite 2 will keep on moving or in a circular orbit around this satellite 1. A person seeing satellite 2 on sitting on satellite 1 will see satellite 2 moving in a circular orbit, isn't it? Satellite 2 would appear to move in a circular orbit. So if satellite 2 appears to move in a circular orbit, you have to find out the time period or time taken to complete one full revolution. So what is the time period? Time period is nothing but total distance or 2 pi divided by angular velocity. Now the angular velocity that I have to use out here is nothing but relative angular velocity of 2 with respect to satellite 1. That means what? I have to find out the angular velocity of satellite 1 with respect to Earth. I have to find out the angular velocity of satellite 2 with respect to Earth. And then I have to find out relative angular velocity of satellite 2 with respect to satellite 1. Understood? And then time rate is equal to 2 pi by omega relative. Fair and fine. This one should be understood. This is the approach that I'm going to do in the question. Okay. So what is the angular velocity of satellite 1 with respect to Earth? I can simply use m omega square r. Okay, centripetal force is equals to g m into mass of Earth. Okay, let mass of Earth be capital M. Mass of Earth by r square. Okay, just take any distance. Okay, or the formula for orbital radius would come as omega square. M and M would get cancelled. Omega square is equals to g m by r cube, or omega is equals to under root of g m by r cube. Understood this much? So angular velocity of any orbital thing, orbital satellite or orbital any object. Okay. So orbital angular velocity is given by gm by r cube. Okay. And linear orbital velocity is given by gm by r. Okay. Angular orbital velocity is given by gm by r cube. Fair and fine. This much is understood. Okay. Now in the question it is given that this distance, okay, distance between Earth and satellite 2 is 7,000 kilometers. Or let's name this x. This x is nothing but 7,000 kilometers. I'm using x. Okay. And this distance between satellite 1 and satellite 2 is given as delta x, which is nothing but 70 kilometers. There are some other doubts, sir. Why not y or any other variable? Why delta x? See, we can easily observe that 70 kilometers is much lesser than 7,000 kilometers, isn't it? Okay. So somewhere you get the intuition that some approximation is going to happen. Okay. So instead of using different variables, if you use delta x, it would be much easier to look at the equation. Okay, in terms of approximation. Or you can easily associate the equation with approximation. See, I have to approximate out here or out here. Understood? There is no other reason to use delta x as a variable. We are not going to differentiate out here. Anything. Okay. So what is the orbital radius of satellite 1? Omega 1. Omega 1 is nothing but g into mass of Earth by r cube. Okay, r cube. R cube is nothing but this much distance, or distance between satellite 1 and Earth, and this much distance is nothing but x minus delta x, isn't it? Distance between satellite 1 and Earth is nothing but x minus delta x. So if we apply x minus delta x instead of r, I'll get x minus delta x whole cube. Okay. Similarly, angular velocity of satellite 2 is nothing but gm by, how much is this much distance? X only. Distance between satellite 2 and Earth is nothing but x, gm by x cube. Okay. Now I'll further simplify. See, first I'll solve the physics part of the problem, then I'll solve the equation part of the problem. Okay. So physics part of the problem is I found out omega 1 and omega 2 with respect to Earth. Okay. I need to find out time period. Now there will be two scenarios of time period. Why? See, both the planet can move in same direction. No? Planet 1 is also going upward, planet 2 is also going upward. That means planet 1 is also rotating anti-clockwise, planet 2 is also rotating anti-clockwise. Okay. So there are two cases of this scenario. Both the planets are moving in same direction. Both the planets are moving in same direction. In same direction. Okay. That means planet 1 will also move upward, planet 2 will also move upward. So when both are going upward, there will be a rotation, and that rotation, suppose that rotation, okay, this rotation, suppose I'm fixing satellite 1. Satellite 2 would be rotating somewhat like this, isn't it? Satellite 2 would be rotating somewhat like this. So the angular velocity of satellite 2 out here is nothing but relative angular velocity as seen by satellite 1. And relative angular velocity of satellite 2 as seen by satellite 1 is nothing but omega relative is nothing but omega 2 minus omega 1. That means when the planets are moving in the same direction, okay, angular velocity of satellite 2 with respect to 1 is nothing but omega 2 minus omega 1. So time period would be t is equals to 2 pi by omega 2 minus omega 1. So out here time period would be 2 pi by omega 2 minus omega 1. Now the second scenario is when both the satellites are moving in opposite direction. Either one is moving up and two is moving down, or two is moving up and one is moving down. So what would happen? See, if one is moving up, two is moving down. This appears to go faster, no? The relative velocity of 2 appears to be faster, no? Why is that? Because out here the relative velocity gets added. So in case 2, when the planets, when the satellites, not planet, satellite, okay, are moving opposite to each other, are moving in opposite direction. Opposite direction. When the satellites are moving in opposite direction, what would happen? The relative velocities will get added, no? See, just simplify this process. When two cars are going in opposite direction, what is the relative velocity of one with respect to other? The relative velocity, the velocities get added, no? To find out the relative velocity. Same kind of thing is happening out here. In the first case, omega 2 vector was in this direction, omega 1 vector also in this direction. This is my right hand, okay? Okay. So relative angular velocity is nothing but omega 2 minus omega 1. In the second case, what is happening? Omega 2 vector is in this direction, while omega 1 vector is in this direction. So to find out relative velocity, both the values will get, or both the angular velocities will get added. So in case 2, omega relative would be nothing but omega 2 plus omega 1. Omega 2 plus omega 1. In case 2. In case 1, when both the planets are moving in the same direction, relative angular velocity of 2 with respect to 1 is nothing but omega 2 minus omega 1. In second case, when the planets are moving opposite to each other, relative angular velocity is nothing but omega 2 plus omega 1, isn't it? So out here time period would be nothing but 2 pi by omega 2 plus omega 1. So out here the physics part of the problem ended. Okay. Now we'll go to the mathematics part of the problem. Okay. Now listen to me very carefully. Okay. The mathematics part of the problem. We can see that 70 kilometer, that means this 70 kilometer and 7,000 kilometer. 70 kilometer is very less compared to 7,000 kilometer, no? So the satellite are very near to each other. So we can do some kind of approximation. It is not easier to calculate this value, no? Okay. Now I'm telling one thing, listen to me very carefully. In your entire syllabus, whenever you have to ignore a certain term, you always can use binomial expansion. Okay. There is no exception. Whenever in your syllabus you have to use any kind of approximation, you can blindly use binomial expansion. What I'm trying to say is, suppose I'm taking this term. Okay. I'm taking this term. What is this term? Omega 1 or this. Let me copy this term. Okay. I'm taking this term and I'll simplify this term. Okay. I'll simplify this term. Let me just simplify this term. Omega 1 is equals to under root of gm divided by x minus delta x cube. Okay. X minus delta x cube, I'll simplify separately. Is equals to, I'm taking x common, 1 minus delta x by x whole cube. Isn't it? Or I can write this as x cube 1 minus delta x by x whole cube. Isn't it? Okay. See this part, 1 minus delta x by x whole cube. Okay. So I can write this as delta x 1 minus delta x by x whole cube. Okay. Now I just want to take this term 1 minus delta x by x whole cube outside the square root. Okay. It will be nothing but omega 1 is equals to under root gm by x cube. Okay. And 1 by 1 minus delta x by x whole cube. Now if I want to invert this one, I have to invert this one. What will happen? This will be nothing but 1 minus delta x by x. Achha. Out here it will be 1 minus delta x by x whole cube. Okay. And I'm taking this outside the square root. No, if I take this term outside the square root, what would happen? Divided by 2. Now if I want to take this entire term to the numerator, what would happen? A minus would appear out here. Okay. I'm just solving equation. This is nothing different. Okay. This is taken at the numerator. So minus would come out here. Minus 3 by 2. If 1 by x can be written as x to the power minus 1, no. Same thing I'm doing out here. 1 by this term to the power 3 by 2 is nothing but this term to the power minus 3 by 2. Okay. If you do reciprocal, that is nothing but raised to the power minus 1. Understood this much? Okay. Now the important part, see. We know that delta x by x is much lesser than 1. So is a theory of binomial expansion. Binomial expansion. And whenever in your entire syllabus, you have to ignore anything. Okay. You most of the time, and 99% of the time, you use binomial expansion. What the theory says is that 1 plus x to the power n, okay, where x is much lesser than 1, can be written as 1 plus x, plus nx plus n into n minus 1 x square divided by 2 factorial, okay, plus n into n minus 1 n minus 2 x cube divided by 3 factorial, and so on. Okay, this term will go on and on. Okay. Now, one thing to note out here is, suppose I used a calculator and found out some values, 1 plus x to the power n. Okay. Now I'm using calculator and finding out the same values. I cannot calculate up to infinity, no? So what this term signifies is, see, whenever I'm doing like this, if I take only the first term, okay, we'll get some approximate value. If I get first and second term, I'll get more accurate value. If I take first, second, and third term, I'll get more accurate value. Okay. So as I'm increasing or as I'm adding up higher orders, the accuracy of the answer is getting more accurate and accurate. Understood? So most of the time, whenever you ignore something, suppose I am to ignore 1 plus x to the power n. Okay, I am to ignore the value of x. X is very much lesser than 1. So I'll ignore x, 1 to the power n. So just take the first term. We'll ignore the remaining. Okay. And the remaining cases in your syllabus, okay, they have just taken the second term. So these higher order terms are always neglected in your syllabus. Okay. Higher order terms. Higher order terms to be neglected. To be neglected. Understood this much? Okay. Most of the time you use only one. In some of the cases you use both 1 plus x. Okay. Now we'll apply this formula out here. Okay. In 1 minus delta x by x to the power minus 3 by 2. If I do binomial expansion of such 1 minus delta x by x to the power minus 3 by 2, I'll get nothing but 1 minus of minus 3 by 2 into delta x by x plus some higher order terms. Okay. which is equals to 1 plus 3 by 2 delta x by x. Okay. There is no question in my syllabus that I have seen that have used higher order terms. Okay. In most of the cases, the first two terms are very good for approximation. Okay. Okay. Now, if I use this term out here, okay, omega 1. Omega 1 is nothing but under root of gm by x cube into 1 plus 3 by 2 delta x by x. Okay, omega 1 is nothing but this value. Okay, and fine. So let me write down the value of omega 1. Omega 1 is nothing but how much? Under root of gm by x cube into how much? 1 plus 3 by 2 delta x by x. 1 plus 3 by 2 delta x by x. Okay, I'm repeating once again. Whenever in your entire syllabus you have to do some approximation, you can always use binomial expansion. And in most of the cases, when you simply ignore the value of x, the condition for this expansion is x is much lesser than 1. Okay, outer condition out here is x is much lesser than 1. Okay, suppose you want to ignore the x altogether, you just use the first term. Suppose you want a little bit more accurate answer, use first term plus second term. Suppose you want more accurate answer, use first term plus second term plus third term. Okay, as I increase the order of terms, the accuracy gets added and added. Understood? So if I average this out or approximate this out, I'll get my answer to be this one. Sir, why did you use binomial expansion? Wasn't this algebra pretty means as it is? See, we use binomial approximation because it is easier to calculate. Okay, so this is supposed to be easier to calculate than this one. This one is more accurate value. This one is easier to calculate but approximate value. Understood the difference? Okay, so omega 1 is nothing but approximate value of omega 1 is nothing but 1 plus 3 by 2 delta x by x. Omega 2 is nothing but gm by x cube. Now what is omega relative or omega 2 minus omega 1 when both are moving in same order? Omega relative is equals to omega 2 minus omega 1. Okay, or omega 2 minus omega 1 is nothing but gm by x cube minus gm by x cube 1 plus 3 by 2 delta x by x, or is nothing but gm by x cube minus under root of gm by x cube 1 plus 3 by 2 delta x by x. Now this portion will come as negative. Do you know why? Because by logic we can already see one is this satellite one is nearer to Earth, so it will go much faster, no? So when I did omega 2 minus omega 1, that means what? Omega 2 minus omega 1 means what? The direction of satellite or the relative velocity of 2 with respect to 1 would be in negative direction. So the negative that appears out here, okay, omega 2 minus 1 is nothing but the direction of the relative angular velocity. Okay, nothing more, nothing less. So even my time period can come as negative, but do not worry about that. It is nothing but that denotes the direction of the angular velocity. Okay, okay. Out here, time period, or let me just simplify. Okay, let me simplify this one. I can take gm by x cube common out here. See, I can take gm by x cube common out here. So if I take gm by x cube common, I'll get nothing but gm by x cube 1 minus 1 minus 3 by 2 delta x by x, isn't it? Okay, and I'll cut 1 and 1. 1 and 1 will get cancelled. So it would be nothing but under root gm by x cube into minus 3 by 2 delta x by x. Or time period will be nothing but 2 pi by omega relative. Omega relative is nothing but gm by x cube, okay, into minus 3 by 2. Okay, minus 3 by 2 delta x by x. Okay, this minus I'll send it out here. Okay, and negative in time period is nothing but I have taken the direction of angular velocity to be different. Okay, in opposite direction. Understood? Do not worry about the negative out here. Put in the values. G is nothing but 6.67 into 10 to the power minus 11. Mass of Earth should be given in the question. X, distance between Earth and satellite is given as 7,000 kilometers. Okay, delta x is given as 70 kilometers. Okay, if you substitute the values, you'll get the answer. Where's the answer? If you substitute the values, you get the time period. Okay, now the second part of the question, when both are moving in opposite direction, what would happen? The relative angular velocity would get added. So omega relative out here is nothing but relative angular velocity is nothing but omega 2 plus omega 1, which is nothing but under root of gm by x cube plus under root of gm by x cube 1 plus 3 by 2 delta x by x. And when you simplify it, I'm just taking gm by x cube common, gm by x cube Okay, 1 plus 1 plus 3 by 2 delta x by x, or under root of gm by x cube 2 plus 3 by 2 delta x by x. Okay, fair and fine. So time period out here is nothing but 2 pi divided by under root of gm by x cube, okay, into 2 plus 3 by 2 delta x by x. One thing you can note out here is the time period when both the satellites are moving in opposite direction is much lesser. See, this term would be much lesser than this term, isn't it? So if the denominator is more, the time period would be less. Okay, if the denominator is less, time period would be more. And why is that? See, if both are moving, okay, if both are moving in same direction, the relative angular velocity would be a little bit less. But in case both are moving in opposite direction, okay, the relative angular velocity would be much larger. Okay, see the situation out here. Okay, the relative angular velocity when both are moving in opposite direction is much larger than the relative angular velocity when both are moving in same direction. Okay, and when you substitute the values of g and x and delta x, you get the answer. Okay, so this is our question number 218. Start with this question. Okay, in this question, the Earth is out here. Okay, this is Earth. Now suppose a person is standing on the equator of Earth. Okay, the Earth also rotates about its own axis, no? And what is the angular velocity of Earth? Angular velocity of Earth is nothing but 2 pi divided by 24 into 3600. Why is that? Velocity is nothing but total distance or total angular distance by total time 24 hours. In order to convert 24 hours into seconds, we multiply by 3600. In order to convert hour to seconds, we multiply the term by 3600. Okay. Now the question is asking, okay, what are the ratio of forces applicable to this man? So first, let us decide what are the forces acting on this man. See, the person is out here. Okay. Suppose the Earth rotates around Sun. Earth revolves around Sun. So this person out here, okay, this person out here, I'm zooming in on the person, experiences gravitational force due to Sun. Okay, this person out here will experience a gravitational force due to Sun. Okay, gravitational force due to Earth. And if I keep my observer at the Earth, that means what? If someone is observing this person from Earth itself, he'll also experience a centrifugal force, no? Why? Because the observer on Earth is on rotating frame, and every rotating frame has two pseudo forces. One is centrifugal force, the second one is Coriolis force. So F centrifugal. Centrifugal. Now what our question is asking is find out the ratio of forces or ratio of magnitude of forces between gravitational force due to Sun, the centrifugal force, and gravitational force due to Earth. We have to find out the ratio of magnitude of these forces. Some of you might have confusion, sir, what if the Sun was this side, the gravitational force or due to Sun would be on this side, no? I agree on that. Okay, we are not concerned about the direction of force. We are only concerned about what is the magnitude of gravitational force due to Sun, gravitational force due to Earth, and centrifugal force on the equator. Understood? We have to find out the ratio of these forces. That means we have to find out. So gravitational force due to Earth is nothing but G into mass of Earth into mass of this man, isn't it? Mass of this man divided by R square. But capital R is nothing but the radius of Earth. Okay. This is gravitational force due to Earth. Similarly, gravitational force due to Sun. Gravitational force due to Sun is nothing but G into mass of Sun into mass of human into distance between Sun and human. That means this distance x is nothing but distance between Sun and this human. Okay. And centrifugal force. That means if I'm observing, or if my observer is at Earth and he's observing this human, the centrifugal force on human should be nothing but F centrifugal is nothing but mass of human into omega square. Omega is nothing but rotational velocity of Earth or angular rotational velocity of Earth into R. R is radius of Earth. Okay. Now see, I gave you the formulas. From your JEE perspective, you are not required to memorize the values of mass of Earth, mass of Sun, and or distance between Sun and Earth. However, you are required to know from competitive perspective that which one of these forces is greater. So I'll show you. Gravitational force due to Earth is much greater than centrifugal force on the human. is much greater than gravitational force due to sun. Okay, if you substitute the values and find out the ratio, you'll find that gravitational force due to earth is much greater than centrifugal force on the human, which is much greater than gravitational force on the sun or gravitational force due to sun. Now the question that says is, what are the ratios? See, ratios I'll give you, okay, but you just need to remember this sentence. Okay, you do not need to remember the ratios also. That will be given in the question. Okay, the ratio of F of earth is to F centrifugal is to F sun or gravitational force due to sun is nothing but 1 is to 0.0034 around is to 0.006 or 0006. Okay, 0006. So from this ratio, we can see that gravitational force on Earth or gravitational force due to Earth is much greater than centrifugal force, which is in fact much greater than the gravitational force due to Sun. And why is that? See, even if the mass of Sun is very huge, okay, the Sun contains around 99% mass of the solar system, okay, more than 99%. Okay, but the distance between the human and the Sun is also very large, So divided by x square becomes very large. That's why the gravitational force due to Sun and mass, sorry, due to Sun will be very less compared to the gravitational force due to Earth, because this person out here is much nearer to Earth than Sun. Understood? So this was the question 219. Now this question, okay, this question is asking what height over the Earth's pole the free fall of acceleration decreases by 1%. That is the first part of the question, and the second part of the question is by half. That means out here there is Earth, okay, and if I go some height above Earth, okay, there is mass in, no? Okay. At what height, okay, the value of g out here, this is nothing but acceleration due to gravity, okay. At what height h, the acceleration due to gravity decreases by 1%. That is first part of the question. And at what height the acceleration due to gravity decreases by half. That is second part of the question. Okay. Now the first thing, whenever you used to do gravitational force is equals to mg in dynamics or Newton's law of motion, okay, if you consider, or the assumption, basic assumption was the Earth, okay, was very close to the surface. That means what? G was nothing but, or mg is equals to g mass of Earth into mass of human divided by radius of Earth square. Okay, m and m would get cancelled, and the value of g is to come as g mass of Earth divided by radius of Earth square, which was equals to 9.81 meter per second square, isn't it? But in the chapter of gravitation, we learned that as we go upward, okay, or as we go further from the mass, the gravitational force decreases and decreases. So that assumption is invalid out here. Okay. So what is the formula of G? The formula of G is nothing but G into mass of Earth divided by distance from the center of Earth. This R is nothing but distance from the center of Earth. Okay. So if the height is given in h, what is the distance from center of Earth? If the radius of Earth is given as capital R, this R will get replaced by R plus h, no? R plus h. So distance from the center of Earth is nothing but G, or gravitational constant, into mass of Earth divided by radius of Earth plus height whole square. So this is the actual formula at whichever height is to find out the gravitational force. Okay. Basically in dynamics or Newton's law of motion and work energy power, whenever it is to do mg, is to consider that this height is very small compared to the radius of Earth. That means 10 not 10 kilometers, 10 meters, 20 meters, 30 meters. The radius of Earth is around 6,400 kilometers. And what is 6,400 kilometers in front of 10 meters? It's very large. So is to ignore this height h, and g mu by r square is to be 9.81 meter per second square. But out here, the height increases so much that it increases by 1%. So in those cases, we have to take in factor of h. Okay. Now how do I do that? Okay. So let me do some more thing. G is equals to G mass of Earth divided by, let's take R common out here. R into 1 plus h by R whole square. Okay. Not like this. R into 1 plus h by R whole square. Or out here, G is equals to G mass of Earth divided by R square into 1 plus h by R whole square, isn't it? This much is understood. Okay. And what is this G? Acceleration due to gravity at height h. So let's write this as GH. Acceleration due to gravity at height h. So acceleration due to gravity at height h is nothing but G mass of Earth divided by R square into 1 plus h by R whole square. And what is G mu by R square? Or what is G mu by R square? It is nothing but acceleration due to gravity at the surface of Earth. Okay. So I can easily say that gravity or acceleration due to gravity at height h is nothing but acceleration due to gravity at surface divided by 1 plus h by r whole square. This much is understood. Okay. Now here we'll do something called binomial expansion. And why is that? See, in physics, this is little bit difficult to calculate. Okay. So in order to make our calculation easier, we use binomial expansion. Okay. And whenever you use binomial expansion, that gives us the approximate value. Understood? So using binomial expansion, this can be written as gh g 1 plus h by r to the power minus 2. And if I expand this term as binomial expansion, 1 plus h by r to the power minus 2, what do I get? I get something like 1 minus 2h by r plus some higher order terms, isn't it? And we ignore the higher order terms. So gravity at height h is nothing but gravity at the surface into 1 minus 2h by r. Okay. See, at the surface, when height was equals to 10, 20, 30, 40, 50 meters or 100 meters, then you used to only take the first term. You take only the first term, gravitational at height h is equals to gravitational at surface. Then as we increase the height, what would happen? We take the second term of binomial expansion. If I increase the height some more, we take the first, second, and third term of binomial expansion. That means as I take more and more terms of binomial expansion, the answer gets more and more accurate. Okay, this much is understood. So a gravitational force at height h is nothing but g into 1 minus 2h by r. And in the question, it is given that acceleration due to gravity decreases by 1%. That means new acceleration due to gravity. Now let's do the first part of the question. New acceleration due to gravity is nothing but old acceleration of gravity minus 1% of old acceleration due to gravity. A new acceleration of gravity is nothing but 0.99 old acceleration of gravity. Okay. If I substitute this value 0.99 g out here, what do I get? Or if I use this formula, I'm using this formula out here. Okay. This formula is used out here. So new acceleration due to gravity is nothing but 0.99 g is equals to old acceleration due to gravity into 1 minus 2 height by radius of earth. So g and g would get cancelled out here. 0.99 is equals to 1 minus 2h by r. 0.99 is equals to 1 minus 2h by r. If I send 2h by r to the left hand side and 0.99 to the right hand side, I'll get something like 2h by r is equals to 1 minus 0.99, isn't it? And 1 minus 0.99 is nothing but 0.01. 0.01. And if I send r to the right hand side, I'll get 0.01 r. Okay, divided by 2. Divided by 2. Okay, and 0.01 can be written as 1 by 100. So this can be written as 1 by 100. So 2 into 100 is nothing but 200. 2 into 100 is nothing but 200. Okay, so let me make this neat and clean. H is equals to r divided by 200. Okay, see the calculation once more. H is equals to radius of earth divided by 200. Now we know that radius of earth is around 6,400 kilometers, and if you divide 6,400 kilometers by 200, we get around 32 kilometers something. Okay, so give the answer by calculating this one. Understood this much? Now the second part of the question. The second part of the question is asking at what height the gravitational force reduces by half. Okay, so at what height gravitational force reduces by half. So we already know this formula that I have used out here is nothing but approximation, no? Okay, and if the gravitational force reduces by half, we cannot use the approximation formula. That means we have to take more and more terms of the binomial expansion. Okay, in physics, however, in case we need more accurate answer, okay, we do not use further terms of binomial expansion. Okay, what we simply do is we use the original formula as it is. Okay, understood? So instead of using, see, in your entire syllabus, 70% cases only you take the first term 1. Okay, and the remaining 30% of the cases you took the first 2 terms. Okay, there are no problems in your physics of 11, 12 standards that you have to use third and fourth terms of binomial expansion. Understood? Okay. So for second part of the question, we need more accurate formula. So you cannot use the approximate formula. You need to use the accurate formula. This formula, isn't it? This formula that was derived from this one, gme by r square. This one. So you need to use this formula, isn't it? Because this is the accurate form of the formula. Okay. So gn is equals to g 1 plus h by r to the power minus 2. We need to use this formula because this is the accurate form of the formula. Now the gravitational force reduces by half. That means new gravity is equals to old gravity minus half is nothing but 50% of old gravity or new gravity is nothing but half of old gravity. So if I substitute out here, new gravity out here is nothing but half of old gravity, isn't it? So if I substitute half g out here, what do I get? Half g is equals to g 1 plus h by r. I'm saying old gravity, but it is nothing but gravity at surface. Okay, this value is nothing but gravity at surface. Okay, so g and g would get cancelled, and it would be nothing but 1 by 2 is equals to 1 plus h by r to the power minus 2. Okay, if I multiply by minus 1, this would become 2. Okay, so this would become 2. 1 by 2 to the power minus 1 is nothing but 2 itself. Okay, and if I square root both sides, I'll get 1 plus h by r is equals to under root 2. And if I send the 1 to the left hand side, I'll get something like root 2 minus 1 is equals to h by r, or root 2 minus 1 is equals to h by r, or h is equals to r into root 2 minus 1. The value of root 2 is nothing but 1.414. 1.414 minus 1 is nothing but 0.414. So 0.414 into r. That means around half the radius of Earth, at height half the radius of Earth, okay, the gravitational force would be reduced by half. That means the value of gravity acceleration due to gravity would be nothing but 4 point something something. Okay, this is 0.414, isn't it? Multiplied by radius of Earth 6,400 kilometers, it will be lesser than half, around 3,000 kilometers. Okay, just calculate the answer using calculator. Now the main important part of the question. Okay, the main doubt some of you might have. Sir, at what part do you use the acceleration due to gravity at surface? Okay, at what part do you just take the first two terms of binomial expansion, and at what terms do you use the most accurate formulas? Okay, means where do you use the first most accurate formula, where do you use second most accurate formula, and where do you use the third most accurate formula, third approximate formula? Okay, see, if you just take the first term, it is least accurate but grossly oversimplified. You take the first two terms, okay, it is not accurate but it is better than the just taking the first term. And if you use the original formula itself, this is the most accurate answer. So you might ask, which questions do you take this, and which questions do you take just ignore the first terms, or in what type of questions do you do that? Okay, see, if the height is around 30 meters to 40 meters, or if the height is given in meters in your question, okay, you just take the first term. That means gravitational force at height h is nothing but gravitational force at surface. Okay, if the height is around, let's say 70 kilometers, 80 kilometers, 90 kilometers, 100 kilometers, okay, that means if the height is around 5% or 5% or lesser than 5%, then the radius of Earth, okay, if the height that you are calculating is lesser than 5% of radius of Earth, then you can take the first two terms of binomial approximation. Okay, and if the height is around 1,000 kilometers, 2,000 kilometers, 3,000 kilometers, then you have to use the most accurate formula, or accurate formula itself. Understood? These are the three scenarios. Okay, so this is our question number 2.220. In this question, we are required to find out the maximum height of a particle that has been projected upward with velocity v0. Okay, so whenever in mechanics, whenever is to find out maximum height, how is to apply? Is to apply a certain formula. No, v square is equals to u square plus 2x. Suppose this was Earth and a ball was thrown vertically upward with some initial velocity, let's say v0. What is the maximum height of this body? Is to find out using this equation. V square is equals to u square plus, minus 2gs. Minus 2gs. And do you know where this formula came from? This formula is nothing but the radiation of work energy theorem. How is that? See, if I send v square minus u square, is nothing but minus 2gs. Okay, if I multiply half mv square minus half mu square is equals to minus half into m into 2gs. Okay, 2 and 2 will get cancelled. It will be minus mgs. So minus mgs. So work energy theorem is nothing but final kinetic energy minus initial kinetic energy is equals to work done by gravitational force. So final kinetic energy becomes 0, and you usually get u is equals to how much? Under root of 2gh. Okay, or initial velocity is equals to, v0 is equals to under root of 2gh. Or if you want to find out how height is equals to u square by 2g. Both are the same thing. But in this case, we'll apply the same formula. The only difference out here is the value of gravitational constant is not same. See, in mechanics, whenever you used to apply this formula, there was an assumption that the value of g is same. That means at whatever height, you go, the value of g remains 9.81 meter per second square. But in this question, as I increase the height, the value of g will also change. So in this question also I'll apply work energy theorem, but in a little bit different manner. Okay. So at maximum height, suppose the ball reached out here at maximum height h. Okay. Now what is the kinetic energy of the ball at maximum height? See, whenever maximum height is asked, okay, the velocity at maximum height is always equals to 0. So remember this trick. In any mechanics problem, at maximum height, velocity always becomes equals to 0. Okay, this is the trick that I told you before. I'm telling you now again. So if velocity at maximum height is equals to 0, what is the kinetic energy at maximum height? 0. So kinetic energy at maximum height is equals to 0. Okay. What is the initial kinetic energy? Half mv square. Half m v naught square. So final kinetic energy minus initial kinetic energy is equals to work done by gravitational force. But the work done by gravitational force would not be minus mgh. Okay, it would not be minus mgh. Why? Because the value of gravitation out here is not constant. So what is the work done by gravitational force in the chapter of gravitation, or when the value of height becomes very large? See, the value of gravitational force is nothing but initial potential energy minus final potential energy. And why is that? Potential energy is nothing but negative of work done by gravitational forces, isn't it? So potential energy at this point minus potential energy at this point is equals to work done by gravity at, potential energy at this point minus potential energy at this point. What I'm trying to say is that final potential energy minus initial potential energy. Okay, final potential energy minus initial potential energy. So U final minus U initial, and negative of that value. Okay, negative of that value. Why negative of that value? Because negative of potential energy is nothing but work done by gravitational forces. So final potential energy minus initial potential energy, if you multiply that by negative, you'll get the change in kinetic energy. A change in kinetic energy is equals to work done by all the forces. And there's only one force acting out here, it is the gravitational force. And the work done by gravitational force is nothing but negative of final potential energy minus initial potential energy. Okay. So if I redraw my equation, half mv naught square is equals to minus of, what is the final potential energy? Minus g mass of earth into mass of body divided by distance of this body from the center of earth. So if the radius of earth is r, the height out here would be h plus r, or the denominator out here would be h plus r plus h, because you always take from the center of earth. Minus, what is initial potential energy? Minus g mass of earth into mass of human divided by, the body was initially situated at the surface of earth, no? So at this point, or at the surface, the value of denominator out here will be nothing but r, isn't it? So out here it is nothing but r. Now when I solve this equation, minus half mv naught square is equals to minus of minus g mass of earth into mass of particle divided by r plus h, minus and minus becomes plus, plus g mass of earth into mass of human divided by r. Okay. Okay. Out here it is equals to, I have to draw this equals to, it will be clear. Okay. I can cancel out the mass out here. The mass is getting cancelled out here. Okay. Now if I multiply this entire parameter by minus, it will become nothing but how much? Is equals to what? Minus half. Acha, this minus and this minus will get cancelled. Okay. You do not need to multiply by minus. Or half mv naught square, or half v naught square is equals to g me by r minus g me by r plus h. Okay, I just put this before and this minus after. Okay, and fine. Now I need to find out the maximum height. Okay, so I'll take GME common out here. I'm just solving this equation. Okay, I'll just solve this equation out here very quickly. Let's take another slide and let's solve the equation. The equation that I have to solve is half v naught square is equals to GME by r minus GME by r plus h. So half v naught square is equals to GME by r minus GME by r plus h. Okay, so half v naught square is equals to GME common 1 by r minus 1 by r plus h. Okay, if I just simplify this term, do nothing but r into r plus h, and the numerator would get r plus h minus r and r would get cancelled. Okay, and would be left with h by r into r plus h. Okay, so half v naught square is equals to GME by GME by h by r into r plus h. Okay. Now let's invert both the right hand side and the left hand side. I'll invert them, or I'll take reciprocal of them. 2 by v naught square is equals to r into r plus h divided by gme into h. gme into h. Okay. Now let's send. I'll just take r plus h divided by h on the right hand side. The remaining terms I'll send to the left hand side. So 2 by v naught square is equals to gme by r is equals to r plus h divided by h. Okay. Or 2 v naught square gme by r is equals to r by h plus 1. Okay, I'm fine. Okay. Now this one I can send to the left hand side. So 2 v naught square gme by r minus 1 is equals to r by h. Okay. Or h is equals to r divided by 2 by v naught square gme by r minus 1. Okay. This is our answer. But in the back of irodov, this answer is given in terms of g, or acceleration of due to gravity on the surface of Earth, okay, which is 9.81 meter per second. So what is the value of 9.81 meter per second? We know that 9.81 meter per second is nothing but g mass of Earth divided by radius of Earth square, isn't it? We know this value. Okay. Somehow if I want to substitute the value of g, or acceleration at the surface of Earth out in this equation, how do I do that? I'll just multiply the denominator by r and numerator by r out here. So g me by r square, g me by r square is nothing but acceleration due to gravity at the surface of Earth, isn't it? G. Or if I rewrite my equation, h is nothing but r divided by 2rg by v naught square minus 1. Okay, fair and fine. Understood this much. Now, if I want to say, okay, now check out here. When the height is very small, okay, the value of v naught should be very small, isn't it? So when the value of v naught is very small, this term, or 2rg by v naught, becomes a very large quantity. So when this becomes a very large quantity, or 2rg by v naught square becomes a very large quantity compared to 1, we can ignore this one, isn't it? So at very small value of v naught and h, we can ignore the value of 1. Height is equals to r divided by 2rg divided by v naught square minus 1, and this would be ignored. Or height is equals to r divided by 2rg by v naught, r and r would cancel, and height is equals to v naught square by 2g. This is the same answer that you would get when you take the value of acceleration due to gravity constant. Understood? But if you take the acceleration due to gravity variable, this is the actual answer that you get. Okay. So this question is a little bit difficult to read, but I'll simplify it in a term you can understand. Okay. So in this question, what it is saying that this is Earth. Okay. And there is a satellite that is revolving around Earth. Satellite of mass m in a circular orbit. Okay. Now I know the velocity of this satellite. I know the velocity or orbital velocity of this satellite to be v. Okay. I know the orbital's velocity of the satellite to be v. I have to find out the height h from the Earth's surface. Okay. So you can either apply orbital velocity or velocity of or formula for orbital velocity, or you can simply use the equation. But my recommendation is whenever you are solving for JEE Advanced, a little bit difficult type of questions, always go for the concept of the situation and the equation instead of roughly memorizing formulas and then applying. Okay. And this kind of mentality will also helpful in your graduation. Suppose you got selected and you're going to IIT to pursue your engineering. Okay. There will learn that the equation itself are very important. Okay. There will be lots of formulas, the kind of assumption. So this kind of thought process, you must cultivate it from now on only. Okay. The situation and the equation. And you must have a habit of solving equations. So okay, if I know the velocity, okay, I can simply apply gravitational force, or force is equals to mass into centripetal acceleration, isn't it? The gravitational force applied on the satellite is equals to mass into centripetal acceleration. What is gravitational force? G mass of Earth into mass of satellite divided by r plus h, where r is nothing but radius of Earth, isn't it? R is radius of Earth, r plus h whole square. What is the value of centripetal acceleration? M into or mass of satellite into v square by r. What is the value of r? Distance from the center of orbit. What is distance from the center of orbit? Is nothing but radius of Earth plus h. So this is also r plus h. Okay, this r plus h and square would get cancelled. ms and mass of satellite would get cancelled. So let's cancel these two. Let's cancel r plus h. What do we need to find out? We need to find out the value of h. Okay, so 1 by r plus h is equals to v square by g into mass of earth. Okay, let's invert both of them. R plus h is equals to g me by v square, isn't it? Or h is equals to r minus, or h is equals to g me by v square minus r. Okay, now this is the answer that I got, or height of the satellite from the surface of the earth. Now if I want to convert these terms in terms of, see, I do not need to use the value of g. Okay, I do not want to use the value of g into mass of earth. Instead of g into mass of earth, I am to use the value of acceleration of earth at the surface. That is nothing but 9.81 meter per second. So you know that 9.81 meter per second is nothing but g me by r square. I can easily write g r square is equals to g into me. Now if I substitute the value of gme by g r square, by g is nothing but acceleration due to, or acceleration due to gravity at the surface of earth. So we get our value of h is nothing but g r square by v square minus r. If I take r common, h is equals to r into g r by v square minus 1. So this is our answer. Okay. Now this question is about geostationary satellite. Okay. Geostationary satellite. Okay. So geostationary satellite is nothing but, suppose this is Earth. Okay. This out here is Earth. And you are seeing it from North Pole. That means we are going to space, and we're at space, we're looking down at North Pole. So out at the boundary is the equator, isn't it? And the Earth is rotating with angular velocity omega, isn't it? Now you know that at different height, okay, suppose a particle is out here, okay, it is moving in this orbit. The orbital velocity of this particle, or the orbital velocity of this satellite, will depend on the height, or depend upon the distance from the center, isn't it? V is equals to gm by r, where r is nothing but the distance from the center of Earth. Now at certain height or a certain distance from the center, what will happen is the angular velocity of this satellite, the angular velocity of this object, would be same as the angular velocity of Earth. Okay, and at that height, what happens? The satellite is said to be in geostationary orbit. That means the orbit at which the angular velocity of the satellite becomes angular velocity of the Earth, that satellite is known as geostationary satellite. That means a person sitting on the equator or a person standing on the equator will always see the satellite over it. That means when the Earth is rotating and the person came down out here, the satellite would be down out here. When the person is out here, the satellite would be out here, and so on. So the satellite rotates with similar angular velocity with the Earth. So a person standing on the equator will always see the satellite over it. Doesn't matter what time of the day it is, doesn't matter what time of the year it is. And those kind of satellite that always stays over it are called geostationary satellite. Fair and fine. Now we need to find out the linear velocity of the satellite. Okay, the question is asking us to find out the linear velocity of the satellite and the acceleration. That means the centripetal acceleration. Okay, so if this is the satellite, what are the forces acting on it? The forces acting on it are nothing but gravitational forces. And I can say that gravitational forces is nothing but mass into centripetal acceleration. And let the mass of the satellite be m. Okay, so you know that force due to gravitation is equals to mass into centripetal acceleration. What is gravitational force? G into mass of Earth into mass of satellite divided by r. And r is the distance from the center. Okay, r is the distance of the satellite from the center of Earth. Okay, is equals to mass into what is the value of centripetal acceleration? Centripetal acceleration is nothing but v square by r, which can also be written as omega square r. Omega square r. Okay, mass and mass will get cancelled. We know that g me by r square. Okay, not r square, sorry, r square is already out here. R cube is equals to omega square. Okay, but I need to find out the value of r. I do not need to find out the value of omega, because I already know the value of omega. Omega is nothing but same angular velocity as that of Earth, which is nothing but 2 pi divided by 24 hours into 3600. Okay, 24 into 3600 is nothing but amount of seconds in a day. So angular velocity of Earth is nothing but 2 pi radians, or the angular distance, divided by how much? Time taken to complete it. Time taken to complete is nothing but 24 hours. If I want to complete that, or if I want to convert 24 hours into seconds, I multiply by 3600. Okay, so you already know the angular velocity. We need to find out the value of r. So out here, r cube is nothing but g me by omega square. or R is nothing but how much? Gme by omega square to the power 1 by 3. Okay. However, I need to find out the velocity and acceleration. Okay. Velocity is nothing but omega into R. So if I find out the value of R, okay, how do I find out the value of R? See, substitute the value of G, substitute the value of mass of Earth that will be given in the question, and omega you already know. Okay. Suppose you do not know the mass of Earth. You already know the radius of Earth, which is 6,400 kilometer, and Gme by R square is nothing but 9.81 meter per second square, isn't it? You can also use this value to determine out here. Omega you already know. So even when you calculate the value of R, the value of R comes to be around 42,000 kilometer. Okay, so at 42,000 kilometer from the center of Earth, whichever satellite is orbiting in a circular orbit, that satellite would be geostationary satellite. That means I would always see that satellite over my head. Okay. Now sometimes this value is asked in terms of height from the surface. So height from the surface is nothing but 42,000 minus 6,400 kilometer. Okay. So those part of the question is done. In this question, you have to find out the velocity. So velocity is nothing but V is equals to omega into R. You already know the value of omega. Omega is nothing but 2 pi divided by 24 into 3600, isn't it? So omega into R. So V is equals to omega into R. R is nothing but 42,000 kilometers. You have to convert that into meters. Okay. And what is centripetal acceleration? Centripetal acceleration is nothing but omega square R or V square by R. Okay, which is nothing but Gme by R square. Gme by R square, where R is nothing but 42,000 kilometers or 42,000 into 10 to the power 3 meters. Okay. So using these two formulas, you can find out the velocity or linear velocity of geostationary satellite, linear acceleration or centripetal acceleration of geostationary satellite, and the distance from the center of Earth of geostationary satellite. If you want to find out the height, we just have to subtract 6,400 kilometers, which is nothing but the radius of Earth, from this value. Okay, so this was our question 223. So in this question, okay, there is Earth out here. Okay, and I'm seeing it from top of the Earth. That means this is North Pole. Okay, and I'm went above the North Pole and still looking at Earth. So the Earth is rotating with angular velocity of its own, which is nothing but 2 pi divided by 24 into 3600. Now an observer sitting at equator and looking up sees a satellite, okay, appear from west to east, every 11.6 hours. Every 11.6 hours. That means this satellite is rotating its own orbit, isn't it, about Earth? Okay. So when the satellite uses fast, after 11.6 hours, again he sees the satellite out here. After 11.6 hours, again he sees the satellite out here. Okay. The distance of the satellite from the center of the Earth is given as 2 into 10 to the power 4 kilometer. Okay. 2 into 10 to the power 4 kilometer. Or let's name this distance R. We'll put the values later. This is the distance of the satellite from the center of Earth. Using this data, okay, I know that angular velocity of the satellite. How do I know the angular velocity of satellite? Because I know this satellite takes 11.6 hours to complete one full orbit. Okay, after it has completed one full orbit and appeared out here, then only the person will see him again. No, so this satellite takes 11.6 hours to complete a full orbit. This is given in the question. Okay, so we know the time period of satellite. We know the angular velocity of satellite from time period. We know the distance of the satellite from the center of Earth. Using this data, you have to calculate the mass of Earth. Mass of Earth. Okay, I can simply apply G or centrifugal force. Sorry, centripetal force is equals to gravitational force. So gravitational force on the satellite is nothing but G mass of Earth into mass of satellite divided by R square is equals to mass of satellite into omega of the satellite square, means omega square of the satellite into R. Clear and fine. Omega is nothing but the omega of satellite. Okay. Omega of satellite. This is omega of Earth. Clear and fine. Now, can I directly put this omega, or can I directly put 2 pi by 11.6 into 3600 out here in place of omega? No. Why? Because even the Earth is rotating, no? So as the satellite is revolving, the Earth is also revolving, isn't it? So the absolute angular velocity of satellite would be something different than this 2 pi divided by 11.6 hours or 2 pi divided by 11.6 into 3600, isn't it? So you have to find out the absolute value of omega or absolute value of angular velocity of the satellite. Okay, we know that relative velocity of the satellite with respect to a person sitting on the equator is nothing but 2 pi divided by 11.6 hours. 11.6 hours. If I want to convert hours into seconds, I have to multiply by 3600. Okay. So a person sitting on the equator will see this satellite move with angular velocity 2 pi divided by 11.6. Angular velocity is equals to radians or total angular radians divided by total time taken, isn't it? 2 pi divided by total time taken. Very fine. Now, what is the absolute velocity? For absolute velocity, we know that relative velocity is nothing but absolute velocity of the object or absolute velocity of the satellite minus angle or velocity of the observer. And out here, velocity or angular velocity of the observer is nothing but angular velocity of Earth. Because this person will keep on rotating with Earth, no? So this is nothing but angular velocity of Earth. So omega relative, that means the angular velocity as observed by this person, which is nothing but 2 pi divided by 11.6 into 3600, plus angular velocity of Earth. I have seen this angular velocity of Earth to the left hand side is equals to absolute angular velocity of the satellite. That means this angular velocity of the satellite is observed by a non-inertial cloud or someone at North Pole or someone at South Pole. Okay, even at North Pole and South Pole, the person is supposed to be rotating like this. But just imagine some person that is not rotating with the angular velocity of Earth. Okay, the absolute angular velocity of satellite is nothing but relative angular velocity seen by the person from equator plus angular velocity of Earth. Okay, so out here. Now I can substitute this omega out here. Okay, so I'll get my equation as g mass by r square, g mass by r square is equals to omega square r. Okay, or mass is equals to omega square r cube. I'm sending this r square to the right hand side divided by g. Okay, or mass is equals to r cube, that is given as 2 into how much, 10 to the power 4 kilometers. I have to convert that into meters, divided by g into omega square. What is omega square? Omega is nothing but omega of the satellite relative to some person sitting on equator. That is nothing but 2 pi divided by time period of satellite. 2 pi divided by time period of satellite, which is 11.6 hours, plus 2 pi divided by time period of Earth, or 24 hours. Okay, whole square. Okay, tau is nothing but time period of satellite. Time period of satellite as seen by someone on Earth. Capital T is nothing but time period of Earth, or 24 hours or 1 day. Okay, and if you put in the values, you will get the mass of Earth. Now I have few pertinent questions out here. Sir, what would happen if the Earth or if the satellite was moving in opposite direction? Out here, the angular velocity of satellite and the angular velocity of Earth are in the same direction, no? What would happen if the angular velocity of satellite was in the opposite direction? The same thing would happen. Okay, omega relative would be nothing but omega plus omega of Earth. So instead of putting minus out here, you would put plus out here. Okay, if the satellite was moving in opposite angular velocity. So this was our question. Okay. Now in this question, okay, a satellite revolves from east to west. See, in the earlier question, the satellite was revolving from west to east, no? Okay, west to east means whenever a satellite goes from west to east, that means the satellite is traveling in the same direction or rotating in the same direction as the Earth. Okay, and whenever a satellite is rotating from east to west, that means the satellite rotates in opposite direction to the rotation of Earth. Okay, just note it down. Okay, west to east, west to east, same direction as of Earth, or rotation in the same direction as of Earth. Rotation in the same direction as of Earth. Okay, and whenever a satellite travels from east to west, that means the satellite is rotating in the opposite direction to the rotation of Earth. So rotation in opposite direction as of Earth. Okay, in this question, okay, there is Earth out here. We'll again see this Earth from North Pole. Okay, about North Pole, the Earth is rotating with angular velocity omega I, where omega is nothing but 2 pi divided by 24 hours, or 24 into 3600. Okay, now this satellite, okay, this satellite is at distance 1 into 10 to the power 4 kilometer from the center of Earth and is rotating in the opposite direction. In the earlier question, it was rotating in the same direction as of Earth. In this question, the satellite is rotating in opposite direction to that of Earth. Find the velocity and acceleration of the satellite with frame fixed to the Earth. Okay. So first case or first thing you have to do is you have to find out the angular velocity of satellite. See, we already know the distance r. We know the mass of Earth. Okay. If the mass of Earth is not known, the mass of Earth would be given in the question. Okay. We know the mass of Earth. We know the value of gravitational constant. We know the value of r given in the question. We have to find out the absolute angular velocity of the satellite. So if I apply g mass of Earth into mass of satellite divided by r square is equals to m omega square r. Okay, m and m would get cancelled. Omega square is equals to g mass of satellite, sorry, mass of Earth divided by r cube, or omega is equals to under root g mass of Earth divided by r cube. Or absolute angular velocity of Earth is, absolute angular velocity of satellite is nothing but g into mass of Earth divided by r cube. Okay, this is the absolute angular velocity. That means this one is being observed by someone on the North Pole. Say on the North Pole he is not rotating with Earth. Okay, on the North Pole he is remaining static, like this. So someone observing from North Pole or South Pole, someone observing from North Pole who is not rotating with Earth, okay, will see the satellite move with this velocity. Now suppose someone is on the surface of Earth, who is rotating with Earth, okay, what would be the relative velocity of this satellite? Relative velocity of the satellite is nothing but absolute velocity of the satellite minus relative or velocity of the frame or velocity of observer, isn't it? The formula for relative velocity is nothing but relative velocity is equal to absolute velocity minus velocity of observer. Okay. So relative velocity of the satellite as seen by someone on the equator is nothing but how much? Absolute velocity of the satellite, which is nothing but g into mass of Earth divided by r cube minus absolute velocity, sorry, relative absolute velocity of the observer. What is the absolute velocity of observer? 2 pi divided by time period of Earth. But t is nothing but time period of Earth, which is 24 hours. Out here, t is nothing but time period of Earth, which is nothing but 24 hours. 24 hours, this is 11.6. Okay, fair and fine. We got the relative velocity of satellite with respect to someone on the equator. Okay, we have to find out the velocity or linear velocity. Out here, whatever we got was angular velocity. How do I convert angular velocity to linear velocity? We know that linear velocity is equals to omega into r. Okay, or linear velocity relative. That means the linear velocity of this satellite as seen by someone on the equator is nothing but omega relative or angular velocity or relative angular velocity of the satellite into r into this much distance. Okay, or v relative is nothing but, what is angular relative velocity? G mass of Earth divided by r cube into, sorry, minus 2 pi divided by time period of Earth or angular velocity of observer into r. This is the relative velocity of the satellite as seen by someone on the equator. Okay. Now we found out the velocity. We also have to find out the acceleration. So next part of the question is nothing but acceleration. We'll do out here next part of the question. Okay. Let's erase this much. Okay. I'll erase this much. Okay. Acceleration. Now we have to find out the acceleration of the satellite with someone standing on the equator or sitting on the equator. Okay. And I told you before, just visit the topic of Newton's law of motion, last few questions, while I was doing Coriolis force, I told you again and again, our rotating frame, okay, our rotating frame has two pseudo forces. The first one is Coriolis force, the second one is centrifugal force. Coriolis force, the second one is centrifugal force. Centrifugal force. Understood this much? Our rotating frame has two additional forces. The first one is Coriolis force, the second one is centrifugal force. So if I want to apply the equation from perspective of someone standing on the equator, if I look at this satellite, okay, the satellite is rotating with angular velocity omega relative, okay, relative v relative, or moving with linear velocity v relative. That means the velocity out here is given by someone with respect to a person standing on the equator. Okay, if I want to draw the free body diagram, the first one is gravitational force. Okay, gravitational force. The second one is centrifugal force. F centrifugal. Okay, FUGL. And the third force is Coriolis force. What is the formula for Coriolis force again? Minus 2m omega cross v. isn't it? And if I erase the minus, you have to do v cross omega, v cross omega, where v was the velocity of the object with relative to the frame, and omega was the angular velocity of the frame, isn't it? Now see, okay, if I do v cross omega, the satellite is moving in downward direction. Remember, this is my right hand. Okay, the screen might be mirrored, so this is my right hand. Okay, so using three fingers rule, v is downward. Okay, omega is upward. See, if I rotate curl my hand in the direction of omega, the direction of omega or axial vector of omega will come towards me, no? So velocity of the satellite is downward. Okay, omega is towards me. The direction of Coriolis force is nothing but this one, v cross how much? Sorry, v cross omega. So the direction of Coriolis force would be in this direction. Okay, so Coriolis force would be in the same direction as direction due to gravitational force. If Coriolis. Okay, now and out here we have acceleration. So I can write that force of gravitational plus force of Coriolis minus force of centrifugal is equals to mass into acceleration. Out here the type of acceleration will be centripetal acceleration. Okay, or acceleration of the satellite as seen by someone on the equator. I'm writing the equation of the satellite with respect to someone standing on the equator. Okay, so whenever I have a rotating frame, two additional forces or two additional pseudo forces acts out there. The first one is centrifugal force, the second one is Coriolis force. Okay, so force of gravitation is nothing but g mass of earth divided by r square into mass of satellite divided by r square. Coriolis force is nothing but 2 into mass of satellite into velocity of satellite with respect to earth or with respect to the observer. Okay, into v relative. V relative is nothing but under root g me by r minus 2 pi by time period, isn't it, into r. Okay, this is nothing but velocity of satellite with respect to someone on the equator cross how much? Cross omega. Omega is nothing but the angular velocity of earth. Angular velocity of earth is nothing but 2 pi by t. And we already know, see, we already know the direction between angular velocity vector and linear velocity vector is 90 degree. No, satellite will move downward. Angular velocity is in this direction. Okay, so the angle between angular velocity vector and the linear velocity is 90 degree out here. So this parameter into sine 90 is already 1. So I can make this as common multiple. Okay, just that means I'm just multiplying these two terms, and sine 90 is 1. Understood this much? This is nothing but the gravitational force. This is nothing but the Coriolis force. Coriolis force is nothing but 2 into mass of the object into relative velocity of the object that I'm seeing into angular velocity of the frame. 2 into mass into relative velocity of the object as seen by observer into angular velocity of the frame. Okay, minus centrifugal force. So centrifugal force is nothing but m omega square r, or mass of the object into angular velocity, relative angular velocity. Okay, that means the angular velocity as seen by the person. Relative angular velocity into square into r. So out here, a centrifugal would be nothing but mass into what is the relative angular velocity? Under root g mass of earth divided by r cube minus 2 pi by t square. This is nothing but relative angular velocity as seen by someone on the earth, or relative angular velocity of the satellite as seen by someone on the equator of earth into r, where r is nothing but this much distance. M omega square r is nothing but centrifugal force. 2 mv cross omega is nothing but Coriolis force. Fg is nothing but gravitational force. Okay, now if I just simplify these terms, or if I just read these terms nicely, okay, I'll get the value, or I'll get the acceleration out here. Okay, the acceleration as seen by someone on the equator. Okay, so let's solve this equation. So in this scenario, what we'll do is, okay, I'll just erase this much, and I'll also erase. Let this much remain. I'll write this equation. I'll write this whole equation out here. Okay, so g mass of earth m by r square plus 2m into under root gme by r cube. I think it is nothing but gme by r cube. Okay, I think I have not written r cube out here. This r cube was missing from this equation. Okay, gme by r cube. Okay, gme by r cube. Let me see if I made the mistake out here also. No, I just made the my mistake was nothing but not writing the r cube out here. This is nothing but absolute angular velocity of the satellite. No, see, absolute angular velocity of the satellite, r cube, r cube. Okay, so let's get back to my equation. Gme by r cube, gme by r cube minus 2 pi t, or 2 pi divided by t into r. This is nothing but omega r. This is nothing but v relative cross omega. Omega is nothing but 2 pi by t. Okay, okay, fair and fine. Minus centrifugal force. Centrifugal force is nothing but mass into this value. So minus m into how much? G, or m into under root of g me by r cube minus 2 pi by t, okay, whole square into r is equals to mass of satellite into acceleration that is asked in the question. This value is asked in the question. So mass, 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 and mass will get cancelled. Okay, and mass of Earth is already known. Okay, in your case, the mass of Earth would be given in the question. You're not required to memorize the mass of Earth. Fair and fine. So when you calculate this value, or when you calculate this entire equation, you get the acceleration as seen by someone on the equator. Okay,